Engineering 305, example problem 5.9. This is another statically indeterminate problem with axial loading. What we've got is a structure now that's got some stuff going on. We've got some transverse loading. We've got a moment. So let's read the problem statement. It's a pin-connected structure. Pins have zero friction. Is loaded and supported as shown in figure 514A. That's on the screen there. The horizontal member is rigid before the load is applied. It's horizontal before the load is applied. It's rigid the whole time. It does not deflect. Member A, that's the one on the right, is an aluminum bar with a modulus of elasticity of 75 gigapascals and a cross-sectional area of 1,000 millimeters squared. Member B is structural steel bar with a modulus of elasticity of 200 gigapascals and a cross-sectional area of 500 millimeters squared. Well, so I took that, I wrote it down, and it looks like that. All right, so maybe I make that a little bigger. There's our givens, and then what we've been asked is just like the other problems. It's find the stress in the aluminum and the stress in the steel. And so we start punching away, writing equations, right? That's the first part of the problem statement. Once we get that, we'll go back and we'll do the vertical component of the displacement out at the end. But for right now, let's just attack this. So we're going to start out exactly the way we started the other problems. That's the interesting thing. And maybe I'm seeing parallelism that I haven't seen before in previous years. But the stress in the aluminum is equal to the force in the aluminum divided by the area of the aluminum, and the stress in the steel is equal to the force in the steel divided by the area of the steel, not the stress in the steel, it's the area of the steel. So now if you remember, I go, well, how many unknowns do I have? Well, oh my goodness, and then this blows up on me. I've got 1, 2, 3, 4, and to help me out with that, I've got 1 equation, 2 equations. Okay, so my next equation has typically been, I know something about the forces. In this case, I don't know something about the forces. I do know something about the moments. I can write a sum of the moments about C, and that's equal to, well, it's B. Item B is the steel one. So the force in the steel. Now, as I put that load on, then the load in B is going to be upwards, so that's going to cause a positive rotation. So that's going to be a plus the force of the steel, and then times that lever arm, which is 1.5 meters. And then I've got the force in the aluminum, and that's also going to pull it up. And so it's force in the aluminum times 4 meters. And then that's going to be, I've got to subtract the force at P, which is, and I'll just put in the number. I had 150 kilonewtons. I could have put P, and then the distance is 5 meters. And so did I add any unknowns? No, I didn't add any unknowns. So that's good, but I've still got 4 unknowns and 3 equations. So we've got to keep hunting. Let me get that out of the way so you can see that. So you know what the next 2 equations are. They tie back to that delta equals PL over EA, AE, PL over AE. It's play, PL over AE, play. So that is, I want to change my color. That is that delta in the aluminum is equal to P of the aluminum, L of the aluminum over area of the aluminum, E of the aluminum. And then the first thing I'm going to change is I put P because that's the play formula, but I really want that to be F because that's what I'm using so far. So F in the aluminum, length in the aluminum. I'll just rewrite those top 2 terms. And then I also have the deflection in the steel is equal to the F in the steel, L of the steel over area of the steel and the Young's modulus of the steel. All right. So I just bought myself 2 more equations. So that's good. I've got here. There's 4 and there's 5. Unfortunately, along with that, I introduced number 5 and number 6 as far as unknowns go. So I'm still one short. And so here's where, on the other problems, we tied together the deflection of one part of the model with the deflection of another part of the model. And this is a little different. The other ones were tied together with a rigid plate, and so the deflection of one was the deflection of the other. It's not that way this time. What we do know, let me slide that out of the way. Oh, not that. What we do know is that if I look at, actually I'm going to slide this out of the way, I'm going to work over here. If I draw that beam and it's supported here and here when I put this load on, then it's going to stretch like that. And this is delta in the steel, and that is delta of the aluminum. And if I look at, and I call that an angle theta, then I know this distance is 1.5 and this distance is 2.5. So tangent of theta is equal to opposite over adjacent is equal to the deflection in the steel over 1.5, or it's equal to the deflection in the aluminum divided by 4, because those are equal triangles. And that equal triangles, that's how I'm putting together the relationship between what's going on with the deflection of one and the deflection of others. So there's my equation right there. I'm going to highlight that bad boy, and I'll just copy it. Oh, just copy it, and we'll shrink this down, and I'll just drop it right there. Oh, is that a paste? No, that's not what I wanted. Oh my goodness. I want that. No, that's a copy. Oh, hold on. I got to clean up my mess. That was a much bigger problem than it should have been. And I missed my little delta here. I'm missing my delta there. Didn't copy. So now delta in the steel divided by 1.5 is equal to delta of the aluminum divided by 4. That gives me the angle, the relationships I want. And now, in green, I've got my 6th equation. And so I'm all set again. Now I can just go through and solve it. So if I can attack it a bunch of different ways, the first thing I'm going to do is I'm just going to solve for delta in the steel. Sorry, I'm going to go back to black. I think it just highlights better. Delta in the steel is equal to 1. I'm going to write it as a function of delta of the aluminum times 1.5 divided by 4. And now the deflection in the aluminum, well, okay, and then delta of the steel is equal to force of the steel, length of the steel, over area of the steel, E of the steel, is equal to delta of the aluminum, which is force of the aluminum, length of the aluminum, A of the aluminum, E of the aluminum, times 1.5 divided by 4. And now I'm going to say force of the steel is equal to force of the aluminum, and I'm going to move all the terms from steel over. And I'm going to organize all these other terms. So it's going to be the terms that are on the top with the aluminum is a 1.5 and a length of the aluminum. And then I can say my 4 goes down below. And I'm going to put an area of the aluminum and a Young's modulus for the aluminum on the bottom. And then from the steel side, I had to ring that over. I had to ring over the length of the steel goes on the bottom. The area and the Young's modulus goes over the top. So length of the steel, area of the steel, Young's modulus for the steel. Like that. Now we'll start substituting in values. Force of the aluminum times 1.5 over 4. The length of the aluminum, let's take a quick look at the picture. That would be 2. You saw that flash on there. The area of the steel was 500, and I had millimeters squared, and I didn't like dealing with millimeters squared. But here's where it doesn't matter, because when I put in the area, the units are going to cancel right out. Young's modulus for the steel was 200 gigapascals. And now on the bottom, length of the steel, I think it was 1.5. It was 1.5. 1.5 meters. The area of the aluminum is my next term, and that's 1,000 millimeters squared. And then the Young's modulus for the aluminum, Young's modulus is 75 gigapascals. Highlight that. And now you can see the units all cancel out. So that's good. And in fact, there's a lot more that cancels out than just the units. If I take a look, because this is what I do, 1.5 cancels with 1.5. 2 and 500 cancel with 1,000. And that leaves me with the force in the aluminum times 200 over 4 times 75. There was a little dot there that didn't get put on the screen. And that's equal to 2/3 the force in the aluminum. 4 times 75 is 300. Force in the steel is equal to 2/3 the force in the aluminum. Now I can substitute that back into what's at the top of the page there, equation 3. Equation 3. So now I have the force of the steel times, I want to substitute in. I know what the force of the steel is. I want to substitute in for the force of steel. So force of steel is equal to 2/3 the force in the aluminum times 1.5 meters plus the force in the aluminum times 4 is equal to 750 kilonewton. I forgot a meter there. Meters. So the 2/3 cancels with 1.5. Amazing how that works. And I get 5 times the force in the aluminum is equal to 750 kilonewton meters. That 5, was a meter. And so the force in the aluminum is equal to 150 kilonewtons. And now I know the force in the steel is equal to 2/3 of that is equal to 100 kilonewtons. How's that look? Great. Now that I got that, I can go on. I can do the stress in the aluminum is equal to 150 kilonewtons divided by 1,000 millimeters squared. And I really hate the units on that, but that's okay. That's 150 megapascals. It's in tension. We assume that, we knew that, right? Oh, yeah. Yep. And then I've got the stress in the steel is equal to 100 kilonewtons over 500 millimeters squared. Well, that's going to give me 200 megapascals, also in tension. And that's pretty good. That actually calls for a rainbow sprinkle circle. That's pretty good. The last part of this was find the deflection at D, right? You remember if I put the problem statement up, I put the picture up, I got to move the picture over over that. And so find the vertical component of the displacement at point D. And so really what I want to do is it's going to be 5/4 times the displacement at A. So I just need to go back and find the displacement at A, right, which is equal to force in the aluminum, length of the aluminum, over area of the aluminum, Young's modulus for the aluminum. That's the deflection at A. The deflection, because of similar triangles, it's going to be 5/4, 20% more. Sorry, 25% more. And so we just have to punch that in. And if you go ahead and do that, what you're going to get is that this deflection is 4 millimeters. And then the deflection at D is equal to 5 millimeters. All right? That's not a bad problem. It does really follow the same pattern that we've set up on the others, where we're going to start with, it's asking us for stresses, and so we start with those equations for our stresses, and then we start with a force equation, and we can find a force equation, and then that's when we need to move to a deflection equation, and then there's got to be something tying our deflections together. And once we've got all of that, now we're into 6 equations and 6 unknowns, but we can do the math. All right? This is one of the hardest sections, I think, in the book. And we're going to do this 2 more times, actually. We will do it 2 more times. We're going to do this. Sorry, I think my audio got bumped. My audio went up there. We're going to do this with torsion. There are going to be torsionally loaded problems that are statically indeterminate, and there are going to be beam problems that are statically indeterminate. So they take a little bit of insight into the physical situation. You have to look at the situation and see how those systems are related. I think I did the last part of the problem right with it covered with the problem statement. Anyway, there's your answers for that. Sorry if I had you covered. All right, hope you're doing well. See you in class.